at least the first.
Bonjour. Ah oui, ça fait longtemps, oui.
Bonjour.
Le réseau de surveillance des infrasons,
Oui.
le système international de surveillance des infrasons.
Pourquoi? Pour le AMS?
En français,
Traduction
en
AMS?
français. C'est le
non.
système international de surveillance des infrasons.
Non, système de surveillance international.
SSI. Ah oui, SSI.
International,
SSI.
et c'est la composante infrason.
Yeah, okay.
Il faut qu'on
Les
commence.
capteurs infrasons.
On doit commencer parce que c'est
Oui.
là. Pardon.
It's okay. It's already prepared. It's prepared. Yep. You went from 1 to 5.
Good morning. So welcome to the T1.1 session on the atmospheric dynamics. We'll start right away because we cannot allow too much time for introduction. So we will have 6 talks this morning and the poster preview at 10:30. And I just want to mention as well that we will have some more talks in the afternoon in this same room, and we'll repeat it, but there will be also the poster preview, and we would like the poster presenters to be at the poster at between 2:30 and 3:30, so that we can come and visit them, and we invite all of you in the room to go and see the posters. So without further ado, I would like to call Mr. Hiss to present the first talk of the morning on application of advanced data assimilation techniques to improve atmospheric transport and dispersion predictions. Thank you.
Okay, good morning, everyone. So my name is Nick Heath. I'm a research meteorologist with the United States Air Force Technical Application Center. And so I'm just going to be talking about applying different data assimilation techniques for atmospheric transport and dispersion. So most of us are probably aware that if we're going to be modeling transport and dispersion of radionuclides in the atmosphere, we need good meteorological input. And so one way that we do that is we do a lot of data assimilation. So we try to bring in all the available observations we can to make the model as close to reality as possible. When we're looking back in time, and what's typically used in transport and dispersion is something called 4-dimensional data assimilation or nudging. However, the weather forecasting community typically uses more advanced data assimilation techniques, which I'm going to explain next. So here's just a kind of schematic of 2 flavors of data assimilation. So on the left is the nudging approach. And so basically what we're doing here is we're just doing continuous assimilation over time, relaxing the model toward observations. So you see the green would be a forecast without nudging, and then the red shows that we just kind of gradually nudge the model toward the observations. This is kind of a simple approach, and it allows you to nudge temperature, humidity, and winds. On the right is a more advanced 3-dimensional variational approach, and this is something that's commonly used in weather forecasting. And the idea here is we're trying to get the best analysis of the atmosphere as we can for a forecast. So we basically take all observations that are representative of a single time, and we bring those into the model and get the best analysis we can. And the benefit of this is that we can use a lot more observations. So we can use remotely sensed observations from, for example, from satellite or from radar. So kind of the two differences here is nudging is continuous, but it's a simple approach, whereas the variational is just getting an initial state for the model, but it allows you to bring in a lot more observations. So the question we wanted to ask is, can we find a way to apply the more advanced techniques in a way that's applicable for transport and dispersion? So the model we're running is the Weather Research and Forecasting Model WRF. We set up 3 domains over the western half of the United States, centered over Colorado there, the 3-kilometer, the highest resolution domain. And you can see some of the other settings for WRF. I won't go into too much detail, but we can talk offline if you're interested in how we set up WRF specifically. So we came up with 3 data assimilation experiments, the first one being nudging, using the nudging technique. The second one, we did a cycling 3D VAR. So as I mentioned in that little schematic, what the variational techniques do is they get the best initial state for the model. So to make this applicable for transport and dispersion, what we have to do is basically do the assimilation, run the model for 6 hours, and then bring in all the available observations we can, run it again for 6 models, bring in all the observations we can, and basically combine that into one continuous time series for transport and dispersion. And then the bottom one is just the same exact thing, except for we use something called DFI, or a digital filter initialization, which just smooths out model imbalances, which was motivated by these plots here. So what this is showing is the surface pressure tendency, which can just be thought of as an index for the model imbalance. And so these plots are here actually the reason why the transport and dispersion community typically uses a nudging approach. Because if you see in the top there, the green line is nudging, and you see a lot of imbalance at the beginning, and then it just kind of levels out. However, when you're doing the cycling approach and bringing in a lot of observations, continuously restarting the model, you get these huge jumps, so you get a lot of discontinuity. And so for atmospheric chemistry or for transport and dispersion, you can't really have those discontinuities. And so the digital filter initialization shown on the bottom is just a way to try to remove some of that imbalance to try to smooth out the time series for the transport and dispersion. The transport and dispersion case we're studying is the Colorado Springs tracer experiment. For this case, we had 3 release locations, which are shown as those little black dots. And then we have releases on 3 different days in October of 2010. And so we have a total of 9 different releases that we can validate against. And then the samplers were basically deployed based on the predominant wind direction. The transport and dispersion model we're using is HYSPLIT, the hybrid single particle Lagrangian integrated trajectory model. And that's just some of the settings. We just tried to set it up to match with the observations as close as we could. So let's start by just looking at the meteorological evaluation. So again, the point of the data assimilation is to make the MET as good as it can to then drive the transport and dispersion. So we'll start by evaluating that. What these plots are showing are domain averaged statistics. The top is the bias, and then the bottom is the mean absolute error. And this is just a time series over the model simulation. And then the little red asterisks just showing which one performed better. So for 2-meter temperature, nudging did slightly better for the bias, and then cycling did slightly better for the mean absolute error. For 10-meter wind speed, which is obviously going to be important for transport and dispersion, nudging did slightly better for both. And then looking at the directional components, so the U and V, nudging did better at 3 of the 4 statistical measures. However, what I really want to show out with these plots is that they're not that different. You can barely distinguish the lines here. So regardless of which data assimilation technique we're using, you get pretty similar results. One thing we can qualitatively say is that the nudging runs seem to have a little bit less variance. You see, which is shown in green, again, the nudging. You see some of the black and blue lines show bigger spikes in some of the statistics, and that could be simply due to those restarts and those constant changes in the model. However, one place that there were actually pretty big differences between the nudging and the cycling were the planetary boundary layer height. And so, as most of us are aware, the PBL is where all the transport and dispersion takes place. So modeling the planetary boundary layer height is very important for TND. And so what we were finding is that the nudging runs were consistently shallower than the cycling 3D VAR, up to between 200 and 500 meters during the daytime. And so with a shallower boundary layer, we're going to get a less dispersed plume and higher concentrations, whereas in the cycling run, we're going to have a more dispersed plume and lower concentrations. And just to give you an example of this, here are some plots showing the simulated plumes for just one snapshot shaded, and then the dots are the observations color-coded to the same scale. And so in this case, the cycling runs here, you see have a much more dispersed plume that doesn't match well with observations, whereas for the nudging run, we see higher concentrations and actually matching fairly well with what the observations are showing, the higher concentration areas and then the kind of gradient toward lower concentrations on the outside. So for this one snapshot, it looked pretty good for nudging. So what we wanted to do is evaluate this statistically. So we use the HYSPLIT final rank score, which is basically just a way to measure the model robustness. It takes 4 parameters and then weights them each from 0 to 1 and adds them up so that 4 would be the worst. 0 would be the worst and 4 would be the best. The 4 parameters it accounts for is the correlation coefficient, which is just the scatter among the predicted and observed values, the fractional bias, which just shows a systematic over or under prediction, the figure of merit in space, which is just basically the plume overlap, a measure of that, and then the KSP is just showing how well the model reproduced the observed distributions of the concentrations, regardless of time or space. So on these next few plots, what we're showing is stacked bar charts where each of those terms are adding up to the final rank on the top. For this case, we're looking at release location 1, and then we have the days separated by the vertical dash lines, and then each of the runs on the bottom. But the take-home message here is on day 1, the nudging run did the best. On day 2, the nudging run did better, and then on day 3, the nudging run did substantially better. When we go to release location 2, kind of the same story. Nudging performed better on day 1, slightly better on day 2, and then slightly better on day 3. And then when we go to release location 3, the nudging run did substantially better on day 1, slightly better on day 2, and then actually the cycling did the best on day 3, but you can see they're very close and very similar. So overall, what do these results tell us? Well, we saw that the nudging consistently outperformed the cycling 3D VAR for this case. The meteorological evaluation was slightly better with the nudging, and then the dispersion results were better in 8 out of the 9 releases. So our kind of takeaway from this is that in retrospective scenarios, nudging provides a simple yet effective data assimilation technique for transport and dispersion that, and it kind of, these results show why the transport and dispersion community have been using it for so long. However, if we're going to be looking in real time, obviously the most sophisticated data assimilation we can use will likely be beneficial, and that's something we're going to look into, how this would play out in real-time forecasts of radionuclide dispersion. And then there's also hybrid data assimilation techniques that bring together both nudging and some of the more sophisticated variational or ensemble Kalman filter techniques. And that kind of combines the best of both worlds. So that's somewhere else that we're also going to be looking into in the future for improving our transport and dispersion simulations. So that's all I have, and I'll take any questions you have.
Thank you. Really, we are in time, so if there's any question in the room. It's early in the morning, I guess. Nobody wants to ask questions. No.
Maybe I can tell something. Yes. Just a short question. This seems to be a very interesting method. And could you tell us a little bit more about future work?
Yeah, so some of the future work.
Planning, your perspective?
Yeah, it's definitely on the bottom dot there, the hybrid DA techniques. So there's been a few papers that have shown that you can combine the ensemble Kalman filter with nudging, and that's kind of a good way, because a big part of what we want to do also is bring in ensembles, bring in a lot of different model approaches to get the spread, because obviously no one single model is going to be correct. And so using the hybrid techniques let us use both ensemble and nudging, and so that's something that we're looking into in the future.
Thank you. Any question? No. Thank you very much. So we'll take our time and we'll move slightly to the next presentation. And before we do this, I just have a small announcement, just to invite you to attend the highlight talks at 2 p.m. today, which will be on the structure and dynamics of the atmosphere. It will be a talk given by Michel Jean. It will be in the Festsaal upstairs. So, and then after that, we'll continue with the poster presentation in the ceremonial salle. So our next speaker will be Patrick Hupe from BGR, and he will be talking about assessing the middle atmosphere weather models using LiDAR and ambient noise, and a case for study for IS-26.
Yes, thank you, Pierrick and Elisabeth. So good morning to everyone. And the study I will present here is a collaborative work which was done within the RISE project together with colleagues from CEA in France and the German Aerospace Center. The idea was to assess middle atmosphere weather models in order to better explain fluctuations in the microgram detections, in the infrasound detections. Micrograms originate from interacting ocean swells on the oceans worldwide, and they can produce false alarms on the one hand in routine infrasound processing, the IDC for example, because they appear in overlapping frequency bands. On the other hand, micrograms are very useful to monitor the middle atmosphere dynamics, as they are more or less permanently detected by the IMS infrasound stations. And on this figure you can see the infrasound microgram detections at IS-26 for almost 20 years, which are the gray dots here. The gray scale indicates the amplitude, and the color scale in the background indicates the propagation conditions for the respective direction, here shown by the effective sound speed ratio, which accounts for the temperature and the winds in the atmosphere, more precisely in the stratosphere. And these effective sound speed ratio values are based on the ECMWF model, which is operational analysis of the European Center for Medium Range Weather Forecast. In general, we see a very good agreement, or seasonally well explained detections. However, there are some outliers in our detections concerning the direction or season and the amplitude as well. And we had the opportunity of doing collocated LiDAR measurements at the infrasound station in the course of the RISE project in 2016. So LiDAR is light detection and ranging. So laser beam is vertically pulsed into the atmosphere, and the backscattered signal is used to derive the temperature profiles. So I will introduce you to the methodology, the data set we used here in the study, and then I will show you an example of the microgram modeling based on the ECMWF model. And after that, I will introduce the LiDAR measurements and the uncertainty inferred from in the weather model. And then I will show you the results of this study. So this is the basic modeling principle. We have a source model for the microbaroms. Then we incorporate atmospheric propagation using temperature and winds from the weather model, but also from the LiDAR measurements to introduce the uncertainty range. And then we are able to model the microgram amplitude, which we compare with the actual infrasound detections at IS-26 in this case. The atmospheric propagation is here the atmospheric attenuation. You can see here on the upper right the attenuation relation proposed by Alexis Lepichon et al. In 2012, which parameterizes the near and far field dissipation of acoustic waves. And these parameters depend on the effective sound speed ratio. So wind, so a long path wind and temperature, which contribute to the effective sound speed. And here we chose the effective sound speed ratio as the maximum between 40 and 60 kilometers in the atmosphere in order to estimate the presence of the stratospheric waveguide, which is the most important for detecting microbaroms. And the input for calculating the effective sound speed was obtained from the ECMWF model, as already introduced. And this model has a special feature that a sponge layer or sponge layers are implemented above 45 kilometers to reduce the effect of uncontrolled wave reflections at the upper model boundary. And the LiDAR measurements we used are obtained from the compact Rayleigh autonomous LiDAR. This is a LiDAR prototype from the German Aerospace Center, which was developed during the RISE project. If you're interested in the measurement principle and more details, you're welcome to attend poster P10 in this afternoon. So far, I want only state that these are very high resolution measurements, and we have had collocated measurements at IS-26 for 7 months in 2016. And of course, we need a source model if we want to model amplitudes of microburms. So we used the acoustic source pressure output of the model from the French Institute Ephemer, which is based on the WaveWatch model from NASA and the surface winds of the ECMWF model. And the resolution of 3 hours provides a daily but also seasonal variation in acoustic source pressure. And here for our modeling environment around IS-26, the strongest sources can be found on the North Atlantic Ocean, where we find dominant frequencies in the model of around 0.25 hertz, which is well in line with the actual detections. So again, the overview, and we made one assumption because the LiDAR was actually located only next to IS-26. So we assumed that homogeneous propagation conditions, and therefore we used the ECMWF profiles at the station only. Here's an example based on the ECMWF model for the monthly mean, more or less. On the left, you can see the acoustic source pressure provided by the source model, and we calculated the integrated attenuation for each grid point here, respective to IS-26. And what you can learn from this figure is, of course, that the best propagation conditions from the North Atlantic Ocean for sources on the North Atlantic Ocean to IS-26 can be found in the winter season, leading to the highest or largest amplitudes detected at the sensors. Nevertheless, we have sources all around the year, so microburms could be detected all around the year, depending on the propagation conditions. But of course, we went into more detail for the modeling. We had time step, or on a daily basis, a time step of 3 hours. Here you can see again this output of the source model on the upper left corner for the most dominant direction, the North Atlantic Ocean. And yeah, we incorporated atmospheric conditions and the distance of the maximum sources to calculate the attenuation here at 0.25 hertz for the dominant frequency. And in the end, we get modeled amplitude or more or less a prediction probability here color-coded for these directions, which are well in line again with the actual detections shown in gray here. So still you can see some outliers or not well-explained detections during summer. However, the amplitude, of course, is also lower here. But we try to better explain these by using the LiDAR measurements. And on this figure, you can see the difference for each night in gray between the ECMWF model and the LiDAR measurements, the temperature profiles. And the main differences can be found above 45 kilometers because of the sponge layers and the damping layers in the weather model. And the mean bias here in red amounts to 12 Kelvin at around 60 kilometers, which can be translated in effective sound speed of around 5 to 8 meters per second. So it's not too much, but of course we need wind information, and unfortunately this LiDAR is not capable of measuring wind, so we used wind data from the Aloma LiDAR in Norway, which showed a similar bias in the temperature measurements, so we assumed that the wind measurements can be applied here. But in general, we computed 100 perturbations for wind and temperature applied to the ECMWF model, which are based on the observations. So we don't have daily-based comparisons, but apply perturbations to the whole time period. And this finally results in different amplitude ranges, which are shown here. The light gray one is maybe the first sight the largest one. It is based on the ECMWF model, and we defined it as 2-day variability of the sources, more or less, as we used the minimum and maximum of 2 days to get an amplitude range. The actual detections resolution here of 3 hours, as long as detections were available. And if more were available, we used the maximum amplitude within a time step, as we also modeled the maximum amplitude for each direction. And the amplitudes modeled here correspond to the observed direction of each detection here for the time steps. So after all, we defined modeling scores. That means, or that are the amount of directions within an amplitude range. And for ECMWF only, this is around 77%, so it's not too bad for the whole time period. But incorporating LiDAR measurements, so the temperature only, this can be increased to 86%. And when even incorporating uncertainty due to winds in the ECMWF model, we have modeling score of 97%. So 97% of the actual detections are then covered by the modeled amplitude ranges. And the main improvement, or the best improvement, can be found in the summer season here. So this amounts to about 60% improvement. So concludingly, of course, winds are more significant than temperature, as the wind deviations measured with the Alamo LiDAR amount to around up to 40 meters per second for the 2 sigma uncertainty, although no mean bias was found. And the impact of the wind uncertainty, which I showed on the last slide, calls for the need of wind measurements, and the development of a mobile wind LiDAR would of course be a good opportunity for this. Of course, we want to increase the duration of collocated measurements, and one example will be shown this afternoon on the poster P6, where we show first results of a related study at IS2, where the same LiDAR was collocated, but for more than 1 year. So this is a good improvement. But we also could think about incorporating other data or other instruments, for example, wind radiometers, and the next RISE project, if the proposal is successful, then the IS-26 station will serve as a pilot station, and this will be a good opportunity for additional collocated technologies, or additional measurements with collocated technologies, and we will be able to show maybe the benefit to equip multiple IMS infrasound stations with LiDARs or other instruments to go from local to more global studies. And then we can show probably that using the uncertainty, which can be found in weather models using LiDAR, that infrasound detections here from microbursts can be better explained, and then we can better explain or deal with false alarms, the routine infrasound processing, but we also use this for monitoring the atmospheric dynamics. Thank you, and I want to make you aware of some related posters. There are several posters also related to RISE, but especially these ones are related to this study, so you're welcome to attend in the afternoon. Thank you.
Thank you. Is there any question for the speaker? This microphone is coming.
So you said you are using Alomar for wind that is quite far away from your station. What are you using? It's a bias and variability? And the difference with this for Alomar?
Yeah, so of course, it's very far away, and it's not Central Europe anymore. It's really Northern Europe, or close to the polar circle. But at that time, it were the only measurements, although in the course of the RISE project, for wind. And therefore we used the perturbations of the wind and not the actual measurements. Because when we use the perturbations in the range of uncertainty, then maybe we can assume that it is similar at the infrasound station in southern Germany. But of course, further measurements would be very useful.
So we can also use now the LiDAR, wind LiDAR from Haute-Provence, OHP.
That would be a good
discuss.
opportunity, yes.
Thank you. And I think we have a second question.
What will be
The
the
microphone, please.
vertical? What will be the vertical resolution of wind data from LiDAR?
So the German Aerospace Center has first plans for such a wind LiDAR, maybe in a simple version for the first prototype. And I think, as far as I know, they also want to achieve a resolution similar to this, so 1 kilometer in the vertical. But I don't know exactly at the moment.
Okay, thank you.
Thank you. We have time for one more question in case. No. So thank you very much.
Okay.
We can move on to the next presentation, which will be by Dr. Chunchusov. It will be talking about atmospheric boundary layer as a laboratory for modeling infrasound propagation and scattering in the atmosphere.
My presentation today will be about atmospheric boundary layer as a laboratory for modeling infrasound propagation and scattering in the atmosphere. At present, the infrasound community has realized that infrasound monitoring of nuclear explosions and natural hazards like volcanic eruptions, earthquakes, meteoroids is not possible without using modeling of the long-range propagation of infrasound signals in the real atmosphere. And such modeling requires detailed knowledge of the stratification of wind and temperature from ground surface to the lower thermosphere up to heights of about 150 kilometers. However, due to strong variability of wind and temperature stratification, usually we don't know detailed profiles, vertical profiles of wind and temperature and during measurement period. And in this case, it is very difficult to model the propagation of infrasound signals. In my presentation, I'll talk about physical modeling of the long-range propagation of infrasound signals in the atmosphere by using stably stratified atmospheric boundary layer and artificial detonation source of acoustic pulses. First of all, I'll talk about acoustic pulse propagation in the shallow waveguide and show the similarity with the propagation of so-called lamp mode generated by nuclear explosions. Then, using stably stratified atmospheric boundary layer, I'll show that it is possible to model the propagation of acoustic pulses in the stratospheric waveguides. And eventually, we'll consider the effect of scattering of acoustic pulses from a fine-scale layer structure in the atmospheric boundary layer and show the similarity with the same effect in the upper atmosphere. First of all, when we are trying to model the long-range infrasound propagation, we deal with similar effective sound speed profiles. These are the profiles which are described by the non-dimensional function of the height normalized by the height scale h of the inhomogeneous layer. And the epsilon here is the vertical jump in effective sound speed within this inhomogeneous layer. And for such similar profiles, it is possible to show by using normal mode solution that the wave field at large distances from the point pulsed source is described by non-dimensional function of the effective thickness of the waveguide, m here, and this effective thickness depends on the vertical jump in the effective sound speed, height scale normalized by the characteristic wavelength of the signal. So we may deal with sources with different frequencies, but if the effective thickness of the waveguide the same, the waveform will be the same at the normalized distance for such sources. And here below, it is shown the evolution of the signal waveform in the so-called Epstein layer when effective thickness decreases from 16 to 3. And when effective thickness becomes much more than a unity, then there is the propagation of only one fundamental mode in the shallow waveguide. And in this case, the waveform of this wave mode is described by the solution of so-called Korteweg-de Vries equation, and it is shown below the waveform, and it looks like oscillating wave train. And it is interesting to note that the same waveform has the signal from the so-called lamp mode generated by nuclear explosion. We see the similarity of the waveforms. And this is confirmed by the comparison of the waveform of the signal from surface explosion of 30-ton TNT, which was recorded at the distance of 310 kilometers from the source. The waveform is shown at the right. And at the left, we see observed form of the lamp mode generated by nuclear explosion at a distance of several tens of thousand kilometers. We see the similarity of these waveforms, which means that we can model the propagation of nuclear explosion by using surface explosion in the tropospheric waveguide. And when effective thickness becomes much more than unity, then there is a large number of modes propagates in the waveguide. And in this case, the rate theory is valid. And we can use stably stratified atmospheric boundary layer and artificial detonation source shown in the picture below. And we can control stratification of wind by SODAR and temperature stratification by temperature profiler. And here at the right, in the upper panel, we show the profile of the effective sound speed, which was obtained from the SODAR and temperature data early in the morning in the atmospheric boundary layer after sunrise. And at the left upper panel, you can see the effective sound speed profile in the atmosphere during the experiments with surface explosion of 20 to 70 ton TNT. And we see that there is a similarity of these profiles in the atmosphere and in the boundary layer. And this leads to the similarity of the ray trajectories. And here are the results of modeling of infrasound propagation of signals in two different directions. In one direction, there is a near surface waveguide, and the corresponding signal is in the panel which is second from the bottom. And in the almost perpendicular direction, there is a shadow zone at a distance of 2.2 kilometers from the source, and we see the single pulse in the panel at the bottom of this picture. Oh, sorry. And the control of atmospheric boundary layer stratification by SODAR allows us to detect the coherent structures and short period gravity wave perturbations in the atmospheric boundary layer. Such coherent structures create very high vertical gradients in the effective sound speed, which scatter the acoustic pulses from the detonation source. And here is shown the detonation source in Armenia, which is simply anti-hail acoustic cannon. And using this source, we studied the effect of atmospheric gravity wave perturbations and coherent structures on infrasound propagation. And here you see in the upper panel the signal from this source at a distance of 2.2 kilometers. We see first the main arrival from the in the waveguide, and 3 weak arrivals, 1, 2, and 3, which were filtered by coherent analysis. And we have shown that these weak arrivals are caused by scattering of the acoustic pulse from the very thin atmospheric layers in the boundary layer, which are shown here. This is very thin layers with high vertical gradients in the effective sound speed. And we were able to retrieve the profiles of these vertical fluctuations within these layers. They are shown here in the upper panel. And then the result of modeling with parabolic equation of the acoustic pulse propagation with using this, with taking into account these perturbations is shown below. It reproduces these weak arrivals. And this is another day when we were able to retrieve the fine scale layer structure in the atmospheric boundary layer. And here is at the left side, the retrieved vertical profile of the effective sound speed fluctuations in the atmospheric boundary layer. At the right side, the vertical profile of the fluctuations in the stratospheric layer between 44 and 54 kilometers, which was retrieved from the waveforms of the signals from surface explosions. These profiles are normalized by the characteristic length scale, vertical length scale, and the effective sound speed fluctuations are normalized by the standard deviations. So when comparing these retrieved fluctuations, we see that it is possible to model the scattering of acoustic pulses from the fine scale layer structure in the atmosphere. And also, there is possibility to model the variations, temporal variations in the effective sound speed. And this effect on the travel time and on the azimuth of propagations. And below you can see at the left side the variations in the azimuth, and the spectrum shows that there are periods like 10 minutes, 3, 4 minutes, and 1 minute, which are typical for short period gravity wave perturbations and coherent structures in the atmospheric boundary layer. So there is possibility to model the effect of gravity wave perturbations on the infrasound propagation in the stratosphere. So my conclusion is that we have shown the possibility to for physical modeling of the propagation of signals from explosions of different power in the atmosphere by studying the propagation of acoustic pulses for artificial detonation sources in stably stratified atmospheric boundary layer. Thank you for your attention.
Thank you. We have time for one question. No question? So I just was wondering, Igor, if so when you show the stratospheric retrieval of the perturbation, did you have also observation for these stratospheric
Yes.
distances?
This is the result of results of the recording of surface explosions from 20 to 70 ton TNT made by Sergei Kulichkov at a distance of about 300 kilometers. So by using waveforms, we were able to retrieve the vertical profile of the effective sound speed fluctuations within this stratospheric layer.
Oh, yeah, okay. Thank you.
So thank you. We will continue with a presentation of Mr. Terzi about the climate change through the use of radioisotopes.
Good morning. The goal of this talk is to provide mainly two messages. So what can CTBT data give in terms of climate change, and especially what cosmogenic radionuclide provide as an information on global warming. And there's two things. The first one, the most important, is that it provides a completely different perspective. So with cosmogenic radionuclide, we can see things that you can't see so easily with traditional meteorological tools. And the second is, because of this different perspective, we can shed lights into areas of the IPCC report where there's low confidence. And we'll look more into that. So how is the... So first of all, what are cosmogenic radionuclide? Cosmogenic radionuclide are formed from the interaction of cosmic rays that come from space. These are highly energetic particles. And they interact with matter once they reach the atmosphere. And when they interact with nitrogen and oxygen, they produce beryllium-7, between other things. And if they interact with argon, then we also get sodium-22. Now, it's been known in the literature for over 30 years that cosmogenic radionuclide, because of their source and formation, they're very good stratospheric, tropospheric exchange tracer. This you see here. Oops. I don't know if you can see the red dot, but basically, you can't see the... Can't see the arrows. Okay, wait, let's go to the next slide. But basically, you have these atmospheric cells, and at the conversion zone of Hadley and Ferrel cell, you have this downward influx of air. And that's where you have this constant income of fresh beryllium. Now, beryllium is better than sodium for one reason. It's homogeneously covering the whole globe. You detect it every day. It's easily to detect. And the half-life, it's 52 days, which means it's short enough that it doesn't accumulate in the atmosphere. That means when we see a strong peak of beryllium, it's fresh, and it's not all beryllium accumulated. But it's long enough that it can be detected by the IMS sensors. So in a very simplified models, we have 3 cells in both hemispheres: the Hadley, the Ferrel, and the polar cell. And the area that we are most interested in, it's, as said before, this one. Yeah? This is the conversion zone between Hadley and Ferrel cell. That's where we have this downward influx of air. While at the intertropical conversion zones along the equator, we have an uprising flux of air, so there it's much more difficult to detect any cosmogenic radionuclide. So, as I said before, it's been known for 30 years that you can use cosmogenic radionuclide for as atmospheric tracer. Now, we wanted to see if as that was already proven in the literature, if we could create, thanks to the radionuclide network, which covers the whole globe, if we could recreate the position of the conversion zones. And that's what we did. As you see here, we took the concentration time series of beryllium and then plot them along the latitude. And what you see, these are the two mountains surrounded by 3 valleys. So the mountains are where we get this influx, downward influx of air. It's like a shower, where we get like a shower of beryllium. And the low, the valleys, that's where we have the upward flux of air. So where it's really difficult actually to get any beryllium. Now, if it's possible to see the position of the conversion zone, then we thought, okay, maybe we can now study meteorological phenomena that are triggered by the movement of the conversion zones, because the conversion zones move northwards towards the summer and southward towards the winter, because it depends on the tilting of the Earth's axis, yeah? So that's what we did, and we published in February this year. We saw that it's possible to use the beryllium as a proxy for seasonal weather prediction. You can have for the Indian monsoon, for instance, a prediction of almost 2 months with an accuracy of plus minus 3 days. And this was a real positive surprise, because we thought it's possible to predict, but we did not expect to have such high accuracy. And especially this year, where the monsoon reached Kerala, which is like the reference point for the monsoon, 3 weeks in delay, we could predict that on the 22nd of April. So if it's possible to see, to predict seasonal weather, then we thought, okay, then it may also be possible to see the changes of weather over time. And just as a warning, this is exploratory work. So that's the hypothesis. You have the stratosphere above, and it's delimited by the tropopause. And the blue lines, the purple lines, are where at the mid-latitudes, where this downward influx of air, where the beryllium is coming down, yeah? Now, these are the position of the cell. What happens when you have an increase of temperature because of CO2 emission? CO2 traps the heat, doesn't release it to the stratosphere, so you have an uprising air that pushes the tropopause high up, but especially it pushes it up at the mid-latitudes. Now, Europe is a hotspot also because of the position. It's exactly between 30 and 60 degrees north. So there we have a very strong effect of tropopause heightening. And the tropopause heightening has a second effect, that it extends the Hadley cell. So basically, by increasing the tropopause at the mid-latitude, the Hadley cell is eating parts of the Ferrel cell, which is an eddy cell. And all this you can see thanks to the many IMS stations. So you have 2 main effects out of this tropopause heightening. The first one is that the temperature gradient between the equator and the mid-latitude is decreasing, yeah, because it's getting warmer at the mid-latitude. So the trade winds are slowing down. So you have a slower atmospheric circulation. But at the mid-latitude, your tropopause is much higher than it used to be, yeah? And this creates a much higher convective energy. So the result is you end up having static weather system and very strong convective energy, which leads to a higher frequency of convective storm, yeah, or just longer storms, because basically the weather is not changing. And this has been proven by many meteorologists, and especially Michael Kunz from the Karlsruhe Institute of Technology, for instance, provided a slide where it showed us the hail, the losses for insurance company doubled in the last 5 years due to hail because of this static weather pattern. So that's in accordance with what the meteorologists are observing. Okay, so what's the link between the tropopause and the beryllium? Basically, this is a work from DeLake from 2005. The beryllium is related to the tropopause because it increases with highness. So as I said before, the higher your tropopause, the more beryllium from the stratosphere is taken into the troposphere and then gets part of this, gets transported through the atmospheric circulation and can be measured at the station of the IMS. One of the advantages of the these radioisotopes is that they are detected by physical station from the IMS, and they're detected daily, and they're detected now since 15 years. Yeah? And the same type of study, if you want to look at the tropopause profile, it's done by reanalysis of radiosonde. But radiosonde, it's very expensive, and it's quite unsustainable if you want to do it over a long period of time, yeah? Because you need to have these air balloons in the atmosphere. So there you see how well the two profile correlates. And the disadvantage, of course, is that we have 15 years of time series, which for meteorologists is not very much because you would need 30 years or so. But you can also add to your studies like data from other networks. And for the climate change one, for instance, we got data from the Swiss Radio Protection Bureau, where they also provided us with sodium-22 data, which was very helpful. I will show you in a second for the study of a weakening of atmospheric cells. So again, this is another example. That's a map from SnT, where in purple you have the heightening of the tropopause, and in yellow the lowering down of the tropopause. And for 40 stations of the IMS, where they had the time series longer than 10 years, they match perfectly with the tropopause profiles from SnT. Now, one more thing that is very interesting is that when we re-engineer the data and we look at them from a vertical point of view, so we have the days of the year on the horizontal and then the years on the vertical, and the concentration on the z-axis, what you see is that for some location, not just the beryllium is either increasing or decreasing, but the period is extending over time. So in certain cases, we have an extension of beryllium increase by 30%. And that is in agreement with drought trends. So because beryllium increases when you have very high tropopause, and you have a very high tropopause when the air is very hot, so during the summer. And the fact that we see this increase, it's a clear indication of climate change. And this would be very helpful for, as a country profile, for instance, yeah? If you want to know for your agricultural planning, what is your trend for the future. This was a study done thanks to the Swiss Radio Protection Bureau, where you have the ratio change speed between the ratio of sodium and beryllium. So basically, that was based on a study from Philip Steinman. And what you see is that you have characteristic ratios for each season. And if you have a station here and your conversion zone is passing over the station, the ratio changes, yeah, over time. Now, the speed to which the ratio changes gives you an idea of the velocity of these conversion zones, yeah? And the idea is that if the trade winds are weakening, then I should see a much slower ratio change. And that's exactly what you see. You see the peak at the beginning here. This is between 2000 and 2004. So you have this mountain. So you have a very, like a much faster transition of the Hadley-Farrell conversion zone over the station. And then it slows down, yeah? And then it goes into this plane. Now, a consequence of this weakening of the trade winds is that we have these stuck weather patterns, and you see it here, and that's Germany, and that's Sweden. So that's in agreement also with what Michael Kunz said, for instance, regarding static weather pattern observed by the meteorologists. And it's, you see these plateau features, yeah? And here you see how it goes from a sine curve, where you have a smooth transition of the conversion zone over the station, to these plateau features, where it looks almost like the cell is stuck, yeah? And as a conclusion, this is the summary. We believe that the main driver of climate change is this tropopause instability, and that's due to the tropospheric warming. And beryllium can really help in troposphere heightening poleward movements, so this extension of the Hadley cell, in quantifying the weakening of the trade winds, and to visualize this fixed weather structure that have a huge impact in the agriculture. Thank you.
Yeah, we have time for one question. Have you any question? Yes, please.
Petra Seibert, meteorologist in Vienna. Yeah, I appreciate very much that finally a lot of work is being done with the beryllium data. However, there could be many remarks on that. But one thing I really want to correct, namely the radio sound network. It is something that we really need and that we are also going to have in the future. It is not correct to say that it is not sustainable or too expensive or something, yeah? So there is no discussion about abolishing the radio sound network.
No. This was not the question. And actually, we need the radio sound to assess our observation.
Yeah, and
but it's much easier to use for if you want the radio sound. It's very difficult to have it from on a global perspective.
No, it is not difficult. It is something that we have since many decades, yeah? And we are going to have it also in the future. It's the backbone of the global observation system.
Okay.
Okay, thank you very much. And then now it's time to move to the next presentation by Mr. Brown about detection efficiency of the IMS for bolides.
Good morning. I'm going to change the topic a little bit here and start talking about bolides. In particular, I'm going to talk a little bit about the IMS efficiency for detecting bolides. And when I say IMS here, I'm really talking about the infrasound segment of the IMS. So just for a little bit of background, since it's a mixed community, just want to say a few words about some terms that you'll be hearing over the next few days. I'm going to talk about things like near-Earth objects. These are objects that come close to the Earth's orbit. You see the precise definition here, and in fact, these definitions are now used by the International Astronomical Union, so they're generally accepted definitions. Meteoroids are objects typically smaller than a meter in size that orbit the sun and may hit the Earth. They're bigger than a meter in size, roughly. We call them asteroids, but again, that's an artificial designation, but we use both terms. Meteor is the light, heat, and sound shock ionization produced as one of these meteoroids or asteroids hits a planetary atmosphere. And finally, we use the term fireball, bolide, airburst, almost interchangeably. These are just bright, energetic meteors. And in fact, most of what I'm going to talk about today fall in this latter category. All right, so when one of these meteoroids enters the atmosphere, it's moving typically at tens to hundreds of times the local sound speed. It produces a shock in the upper atmosphere. That shock, of course, will propagate outwards, and at great distances, that shock becomes infrasonically detected waves. The fireball itself may also detonate or fragment, and this is just a version of very, very intensive ablation where the physical object essentially collapses under dynamic pressure from the atmosphere. That may produce a fragmentation point, producing a quasi-spherical explosion, whereas the entry itself is producing more of a cylindrical shock. And of course, the energy that's released scales as roughly the blast cavity, or the amount of energy per unit path length, will scale and produce a certain blast size in the atmosphere. And most importantly for our discussion, that scales as 1 over the frequency. So very, very large detonations in the atmosphere typically produce very, very low frequency sound waves. All right, so over the last several decades, there have been quite a few infrasonically detected fireballs or bolides. What I'm showing here is each of the bar graphs is the annual number of bolide detected infrasound measurements, and you can see there were some done in the 1960s, early 70s as part of the AFTAC global network of infrasound stations, and then there was a dry period of a few decades, many of us are familiar with, and then starting about the time the IMS became operational or started to be installed, the rate picked up quite dramatically, and as of now there are over 350 bolide infrasound detections. In fact, this is a lower limit. I'm sure it's much higher. Of these, I should say there are only 4 that have ever been detected exoatmospherically, that is with a telescope first, and then detected through its impact on the ground or infrasonically. So only 4 of these, roughly 400 or so. Infrasound can tell us things about the timing and location of these fireballs, and of course energy. We can't get much information about the path or trajectory of the fireball from infrasound alone. All right, so how often do these things hit the atmosphere? So what I'm showing here is the energy of the bolide on the x-axis going from very small energies, a kiloton, up to of order tens of megatons. The diameter of the equivalent object hitting the atmosphere, which is in the meter to decameter size range on this graph, and then a whole series of observations that try to understand the frequency with which these objects hit the Earth globally. So a meter-sized object hits the Earth somewhere roughly once every 2 weeks. 5-meter objects are roughly once every year, and a 5-meter object has an energy on the order of 10 kilotons. 10-meter objects hit about once every 10 years and are up in the tens to of order 100 kiloton range. And very infrequently, but often over Russia for reasons we don't understand, we occasionally have 20-meter-sized objects that hit. Of course, the most recent of these being the Chelyabinsk object back in February 2013. Those are roughly events that happen every 50 to maybe 150 years. So this gives us a scale at which these things happen. But one of the questions we have is, how often does the IMS and how efficiently does the IMS detect these bolides? And unfortunately, just detecting the odd bolide isn't really enough to give us an idea of efficiency. We need some independent data set that gives us an absolute queued sequence of events where we know the time, location, and energy to compare against infrasound data. And recently, such data has become available in the form of detections by US government sensors. These are reports of bolides that occur on the Earth, typically with energies greater than about 0.1 kilotons, so size is greater than about 1 meter. And we specifically looked at the decade from 2007 to 2017, where there are 346 of these airbursts reported on this JPL Fireball database. And we're using this as a queuing data set to then go into the IMS infrasound data and search for these events. And I should say the data from these US government sensors are data that the events are detected from the ground and in the atmosphere. That is, the events could be on the ground or in the atmosphere. And if the events are deemed natural, that information is passed on to NASA for release. The information typically contains information about total energy, the peak brightness height, and in some cases velocity and or trajectory information. So what we did was we looked at all these events and we tried to determine if an event was reported in the IMS bulletin as an REB. If it wasn't in the REB, so if it was in the REB, we called it a reported or recordable event. If it was not in the REB, but we could find at least one infrasound detection using the JPL information as a queue, we called it detectable. And so here I'm showing all 346 of these events in the upper right, and in the bottom I'm showing 128 of them that were completely undetectable by infrasound. That is, there were no infrasound records either reported in the IMS or that we could detect manually. In particular, only about 12% of all these JPL fireballs, energies greater than roughly 0.1 kiloton, are found in the REB in this time. For energies greater than 1 kiloton, about 40% of all the events are found in the REB. However, if you look at just those that are detectable with 1 kiloton energy and up, we find more than 90% of these bolides are detectable, again, typically from only 1 or 2 stations. So these are the 44 events that were detected in this decade and reported in the REB. You can see a certain distribution in terms of where these events are located. So this brings us to sort of a graph of the detection efficiency. What I'm showing here is the energy of the bolide, and I'm showing a running cumulative ratio running from right to left. So in other words, here I'm saying all events detected in the JPL data set greater than 0.1 kiloton, which would be 346 events, what fraction are in the REB? And in this case, the fraction is very low, about 12%. As you scale to the left, of course, the detection efficiency increases. At 1 kiloton, it's around 30 to 40%. You'll notice there's a dip here, and that's because there's small number statistics, of course, for these big events, and there were a number of big events that were not detected and not recorded in the REB. The detection efficiency is much higher. The current network at 0.1 kilotons detects more than 60% of the meter-sized impactors and in excess of 90% of the 1 kiloton impactors. I should say for each of these events, we can also look at the period at maximum amplitude of the bolides and compare against the JPL energy. We can compare that to the typically used AFTAC yield period relationship. You'll see number one, these are all the bolides. This is the period on the y-axis, the energy of the bolide on the x-axis. I'm showing each individual station here. There's a lot of scatter. The periods are not a tight match to the energy, and that's been known for some time. If you look at a subset that just have multi-station detections and average those, you get a tighter fit. The red line here is the AFTAC fit. It's not too far from what we're seeing. So the point is we can take the energy that we get from the JPL data, and we can compare to the energies we get just looking at period relationships. And I point out in particular an event that happened just last year. This is an event, an airburst that occurred over the Bering Sea. This is MODIS-MISR data showing the dust cloud and evolution over a period of a few minutes. This event was reported on the JPL site as having released 173 kilotons of energy. But if you look at the period globally of this event from many, many different stations, you get a very, very different picture. You get an energy more like 50 to 80 kilotons. And this is actually one of the most dramatic differences between the energy registrations from this JPL data set and global infrasound data. And in fact, we can go ahead and look at all the largest 10 kiloton and larger events that have happened over the last 15 years or so. So here's the event date. This is the energy reported by the JPL systems. There's some other information here about speed. And then I'm showing the number of IMS stations that have detected each of these events. And you'll notice here there's a couple of estimates of energy. These are from slightly different period yield relations. The point to notice is there's a couple of items here in red, one in February 2016 and one in April 2013. These were events that JPL at least reported were over 10 kilotons and did not appear in the REB, although they were detectable infrasonically. I'll also point out two events, the one I just showed you, this Bering Sea event, and another one that occurred in November 2009 in the southern part of Africa that have dramatically different energies from the JPL US government sensor data and what we see infrasonically. And these may be different in part because they were quite different in terms of their characteristics. They entered the atmosphere at much higher speeds. So this already tells us that the IMS, number one, detects many of the bolide events, many small near-Earth object impactors. And number two, it gives us a separate mechanism, a separate type of technology to try to independently check other types of systems that may be giving us energy estimates, gives us a better idea of what's happening with the bolides in terms of the physics and their energetics. So in summary, we see that some larger bolides appear to be missed in the REB. This may be because the energies given by JPL are in fact an overestimate. In fact, many of those objects that are missed in the REB, these two, you'll notice the infrasonic estimated energies are much lower than in the JPL estimate. So it could just be those are much smaller events than we otherwise think. And as a sort of a rough lower limit estimate, we have roughly 40% of all kiloton detonations detected by the JPL systems are reported in the REB. More than 80% of all the 10 kiloton and larger events are reported in the REB. But as detectable infrasonic events, the vast majority of the 1 kiloton and larger events are detectable. Unfortunately, in many cases with the current network, these are with just one station, so it would be very difficult to independently verify whether this is a bolide or not. Thank you very much.
Yeah, we have time for questions, please. We have 3 questions. Okay.
The one here.
We have, okay.
Yeah. Oh, it's okay.
I would like to ask you these events long term, how it will influence our Earth. and human life?
So the question is, how will the events influence humanity long term? Well, certainly a large asteroid impact would have a negative influence on humanity, so we're very concerned about the larger ones. The good news is the current telescopic surveys have found essentially 95% of the 1 kilometer sized impactors. These are impactors that would have global consequences. So for the next 100 years, we know no object of that size will hit the Earth, so that's the good news. The other piece of good news is we're extending our survey limits to smaller objects, down to the few 100-meter sizes, aggressively. So in the next decade or so, we should be able to retire that portion of the risk and say, you know, in the next century, we're not going to see any impacts from these larger events. So the things we won't know about are Tunguska-class 50, 60-meter impactors. There's too many of them for us to catalog those. Those are certainly of concern, but of regional concern. So I would say, again, from a global perspective, we found most of the ones that we have to worry about globally. So this is a good news story. We're actually getting a much better handle on things that could cause global catastrophic consequences.
Yeah, other question? Yeah.
There's one here.
Peter, thanks for your talk. Fascinating. I'll ask a question from the perspective of real ignorance about bolides. Is there much known about the size and morphology of the dust cloud? And where I'm going with this is the IMS keeps a permanent archive of filters, and if you knew the trajectory, location, you could conceivably look at the filters if they had unique morphologies.
Yeah, that's a fantastic point. Bolide science is a wonderful interdisciplinary science. We'd love to get samples of the dust cloud. We have in the past seen LiDAR measurements of the aerosols through a dust cloud. It would be great to recover more of the dust from these bolides on the ground. That would be great. I encourage our folks in the radionuclide community to look at that.
Yeah. And at the end?
Wait from the back.
Peter, you had a slide, I believe 7 or 8, where you showed the detectable bolides
This
that
one?
are no, back. Yep. No, forward one.
Yeah.
There's a very distinct line along the, is it a little bit south of the equator?
So yeah, these, just to be clear, these are the events of the 340 something that were in the REB, so that were detected and got through all the various IDC filtering. I haven't looked at anything about seasonality, or I haven't talked about seasonality here. The winds make a huge difference to detection. So the seasonality is quite profound. I would say this is more interesting. These are the events that were never seen infrasonically. And you can see a lot of patterns here, particularly in the Southern Ocean.
Thank you.
Last question,
So,
quickly.
Is there a certain signature for these events as they're being recorded at the IMS, something with the time width or the way they sound when you listen to them? How do you detect it if it's a bolide or something else?
Yeah, that's a great question. I wish there was some unique signature. I guess the only unique signature is often these are fairly large explosions, and if they're energetic, a lot of their energy is at low frequency, and there's very few anthropogenic sources that would be such high energy. But the waveforms themselves, as far as I know, really are not unique, although there are real infrasound experts around you could ask that. But as far as I know, you can't tell.
And just before we move on, I just want to make a comment. It's very interesting, and it's good to have the JPL as a basis, but it's also incomplete. We know that there's a lot of bolides that are not in the JPL that we detect with the infrasound network, and it would be nice to have the other way.
Yeah, that's a good point. I should say the JPL data, they specifically say they don't report all fireballs, and it's quite clear on their website they only see things that are meter sized and larger, so it's a fantastic point. There are many smaller events that never get on any of these pages. Yeah.
Yeah, interesting. Thank you very much. So we have to move now to the next. We have to move now to the next presentation by Mrs. Hort about NEMO, a global near real-time fireball monitoring system.
Yeah, hi everyone. I'm Theresa Ott and this is Esther Drolzhagen. And we're working together at the University of Oldenburg on this project of a near real-time fireball monitoring system. So it goes in the same direction as the talk before. we're working together with the European Space Agency. Oh, there we go. Yeah, so as you've seen already, a fireball or bow light is just essentially a very bright shooting star, which probably you've all seen before. Yeah, I think Peter covered that very nicely already, so I'm going to skip that. Yeah, here's a nice video of the Chelyabinsk fireball, which was a very big event in the society, which was an asteroid of around 20 meters in size, which hit the Earth with a very high velocity. So this was, as you can see, very bright. It caused a lot of attention. There was a lot of public interest in this event. And it can actually get quite serious. Here you can see the energy of that. Just seems to be a very stable garage door, and it just knocked in. This is from the blast wave, of course, from the pressure wave. And this was actually a real problem. People saw this very nice event, this bright flash, and they went ahead and looked at it through the window, and then this pressure wave hit, and everybody was, the windows broke, and a lot of people were injured. Luckily, nobody died. So why should we care? So far, there were no reports of any death by a meteoroid that are verifiable. But just ask the dinosaurs about it. Could happen any time. Yes, Peter mentioned already. Yeah, so we should be prepared for that.
No, I will continue with a brief introduction into our monitoring system. So we are not interested in all meteors, but only in the very bright fireballs. So these are objects that do regularly impact the Earth's atmosphere, but are too small to be detected by the near-Earth object survey. So as Peter already told, that they cannot see, but in the next decade we can observe them, hopefully early enough to be prepared for them. And these are objects which cause bright fireballs and which cause also a lot of public attention if they happen over a densely populated area. Sure, if they happen over the sea, then nobody sees it. And our overall goal is to validate the flux models of the meteorite fluxes and the near-Earth asteroid population. So to close the gap between large meteoroids and small asteroids, because the meteoroids we can see with our ground-based networks, and the large asteroids we can detect with our telescope surveys. But the intermediate size range, there's still a lack of information. So there's a coordination with FIS, the Fireball Information System from the Space Situational Awareness Center, which is currently in preparation at the NeoCC in Frascati in Italy. And with this coordination, we are interested in all objects with a magnitude of -10 at least, so very, very bright fireballs. And yeah, there are more people or organizations interested in the data. For example, the Planetary Defense Office from ESA and also from NASA, show the International Asteroid Warning Network, and also some national data centers, for example, the BGR, and we have a collaboration with them. In most cases, we receive our data from there, from the BGR. And then there's the public. So we don't want to keep the information for ourselves. So if there was an interesting object, and if we have fast information, then we also are cooperation with the International Meteor Organization. So we have already written summaries, and then it's public, so people can see the results. We always try to compute a size or an energy of the fireball if it was, or of the asteroid, if it was very bright and caused a lot of public attention. So, but this all is work in progress. So we are building up this monitoring system. So we hope that we are faster and to have more information in the future. So the main objective of our NEMO system is that the current situation is as follows. There is a bright fireball. This caused a lot of public attention. A lot of people have seen it. And there is information available about this fireball in a lot of different networks. In camera systems, they can be detected by radar, but also, for example, by this infrasound data from the CTBTO. And we would like to combine all available information in our system to get, in the end, the largest amount of information about our entering asteroid. And here are only some data sources for which we look into these data sources if they have information for our fireball. So we start with the infrasound stations here from the CTBTO. And we are also always comparing with the US government satellite data that also Peter already introduced. We are always comparing if we have a fireball sighting with re-entry prediction databases. So maybe it was a man-made re-entering object that caused this fireball. In most cases, we can separate it if we have videos. These are very long-lasting fireballs. They are taking tens of seconds when they enter the Earth's atmosphere. Then we have the internet and the social media. We are building up an alert system, and this is based mainly on Twitter at the moment. And sure, we have meteor networks. If a fireball was seen with these meteor networks, there's a lot of scientific information already available. For example, the velocity, or maybe even the orbit of the meteoroid. So to only give you some specific goals, over Europe we are interested in also some smaller entering objects. So all objects which are about 10 centimeter in diameter, we would like to know if they happen over Europe. And for this we are mainly collaborating with local meteor networks. For example, this is a map of all stations of the Fripon camera system. They are expanding. We are also trying to cover northern Germany with this camera system. They are looking for bright fireballs. And here's a different example of a fireball that happened over the Netherlands in February. And here you can see that there are a lot of people who have seen this fireball, and they reported just what they have seen. And with this information, if enough people are doing it, we can compute, or the EMO can compute, a trajectory of the fireball. And on a global scale, we are interested in all objects with a diameter of about at least 1 meter. And here we are using mainly the social media, Twitter, but also the Google Alert system, and we are trying to use more different media platforms. Facebook is our next planned step, for example. Yes, sure, the US government satellite data and the infrasound monitoring system, the international monitoring system infrasound data, And if there was a bright fireball, we are asking for the data, and then we look if some infrasound station have seen it. So it's first we receive an alert, and then we are looking into the data. And we are also using the period at maximum amplitude.
Let me introduce to you one of our NEMO events. So usually it starts with a Twitter alert. We found that Twitter is really fast. For some reason, people like to very fastly take a picture or just tweet out, I saw something. So we get a Twitter alert quite early on. This is just one of them. If we're really lucky, we get a picture or video, something very nice. Here, for example, somebody was speculating it might be aliens, which actually happens quite often. This time, actually, they were thinking about very friendly aliens just coming for the World Cup. Usually, it's an invasion or something. Since this happened over Russia, it was very nicely captured on a dashcam, which happens a lot in Russia. Here you can see it again. It's a very bright object. There were a lot of people interested in this, and there were actually quite a few photos and stuff like that coming from this event. Here we just put some of the tweets on. A lot of them get retweeted with similar information, but also with new ones. And it was early on detected with the infrasound system. We also had a look, of course, into the data from the IMS network. We found signals of this fireball on 10 infrasound stations, and with that we calculated an energy of roughly 2.4 kilotons TNT, which we calculated to be about the size of 4 meters. So this was a very nice big event. And the CNEOS JPL data, the US government satellite data sensor, they found an energy of 2.8 kiloton TNT. So this was very similar in the energy estimation. So we're very pleased with that. Yeah, later on we or sometimes get a Google alert or something that is more information regarding additional things that happened later. For example, this were scientists who worked together from different institutes, and they found some meteorite material. So sadly, there was a proof that it was no aliens visiting. Yeah, so let's talk a little bit about our NEMO database. So we started in August of 2017, and from then on we had roughly 300 events so far collected. Here you can see the monthly distribution of how many we saw each month. And we were expecting to see an increase in events, but it turns out it's actually far more difficult to get rid of all the spam that we see than to actually find new events. So we think we actually see all fireballs that are reported. Yeah, here you can see a global distribution. We don't think that there are only fireballs over the US or the Western Hemisphere, but that we just can tap into the social media of the other countries, and also they are not as keen on using those, of course. Yeah, just a short outlook. We would like to add more social media channels, which we have to because others are used, and also implement more fireball networks and get a very nice energy determination. As Peter has talked about it already, it's very difficult to do that. Yeah, and then in the end, of course, get a nice flux for these intermediate-sized objects. Yeah, so references. Thank you for your interest.
Yeah, we have time for one question. No questions, so I would like to ask you one question maybe. The coverage of the IMS network is global now, and you have some country without detection, for example in Africa. Have you some explanation?
Yes, usually we need some starting point for our to look at the infrasound data. So we need, this was just for the social media where we find some tweets or some other sources where they talked about it. And in these countries, usually for Africa or something, not a lot of tweets are going out, not a lot of people are talking online about it. So this was just for the social media, not for the monitoring system, because we didn't look into that if we don't have a starting point.
Okay, I understand, thank you.
Okay.
Thank you very much. So it's the end of the session now, and it's time to start the poster preview session.
Yep.
You have to.
So while we will move on to the poster preview session, which is if you've been to SnT before, you've seen this with the 1 minute slide presentation by all the poster presenters that send their one slide. So I would like to invite poster presenter to line up on the left side of the room, and my colleagues will tell you the order with the poster number. So we have prepared this in a poster preview session by poster number, and all of you have 1 minute, and then it will automatically move on. So you have to be ready to provide this 1 minute discussion. So I think we'll start with, I forgot which number it is, but I guess one of the first. As soon as we are ready, we'll start. We are looking for the first ones, I guess. Looks like we're almost ready.
It's okay?
So we can start. Nicolas, thank you.
Hello. Yes. Good morning. I'm presenting most of the Sandro Mato's work. He's presently just arriving from Stromboli, where he's working on the field. So we just is the continuation of a work that we presented before, that is related to the detections of volcanic eruptions in IS-42 station. Now, with this poster, we present enlargement of this analysis for other stations of the IMS network. So we have several events, and we detected the ones from this case from Grímsvötn volcano in May 2011 in Iceland. So we detect that all the distance from the source from the stations are from the 2,230 kilometers to 6,500 kilometers. And we just compare the detections, IMO observations on the field with our detections and the REB, and they are coherent, and they have some other results that we want to present, and we invite you to go to the poster to discuss in detail. Thank you very much. I'll call the next one.
Yeah, the next one. Okay.
Okay, it's the same approach for the Etna. You know that University of Florence has a local station Etna. So we compare the near field detections with the far field detections IS-42 for several years. Now we extend the observation for other events, for other stations, IMS stations. We have a list of stations. We'll show this in detail in the poster. But interesting to say that in this case, REB doesn't show all of the events we detected in our stations. Of course, we have also slight differences in back azimuths and some differences that we are in a still learning curve of how to analyze this data. So we welcome you to our poster to help us to understand it, to give new ideas to continue this work. Thank you very much.
Thank you.
So in my talk this morning, 1 hour ago, I presented results of a study with collocated technologies, namely infrasound and LiDAR, for the infrasound station IS-26. And here on poster P6, we present first results of a related study at IS-2, so in southern Argentina, where we use the same LiDAR, but we have more than 1 year of observations. So this allows us to better quantify the seasonal effects of the difference between the LiDAR observations and the weather model. And you can especially see interesting results during the equinoxes. So if you're interested, you're welcome to attend the poster P6 in the afternoon. Thank you.
Okay, so in this poster, we present a study of dominant sources of infrasound ambient noise as recorded globally by the infrasound IMS network. We present a methodology to predict directional microbarometer amplitudes at all IMS stations, and there are two main objectives in this work. First, to build, through building a global database of ocean noise sources, first to develop methods to better characterize signals of interest, which might be buried in the ambient noise, but also to provide additional integrated constraints on middle atmospheric dynamics and disturbances in range of altitudes where routine observations are lacking. So you are welcome to see the poster for more discussions. Thanks.
Yes, hi again. So I talked about the LiDAR measurements, and on this poster, P10, the colleagues from the German Aerospace Center show more details on the measurement principle of this LiDAR, the prototype which was developed during the RISE project. And they provide first results on the gravity wave measurements, because southern Argentina is a hotspot for orographic gravity waves. And so these can be very clearly seen in the LiDAR observations and the temperature. So if you're interested, I will be pleased to present these results in the afternoon. Thank you.
Yes, hello everybody. We have used infrasound signals from around 600 explosions covering 30 years in northern Finland to look at the statistical relationship between the crosswinds that we deduced from the infrasound observations with the crosswinds that we deduced from atmospheric reanalysis products. And we found a very nice correlation between the two independent measurements. So I welcome you to poster P11 for more discussions and what we could use this data for. Thank you.
Good morning, everyone. I'm Phil Blom. I do infrasound at Los Alamos National Lab. I have a poster presenting some work that I'm doing jointly with Roger Waxler from the University of Mississippi, looking at constructing statistical propagation models useful for localization and yield estimation methods. A lot of what we're doing now is trying to improve the efficiency of building these models and investigate ways of developing an approach to do event of interest analysis, where you're looking at, instead of a statistical ensemble of, for instance, propagation paths during the wind turn in a given location, propagation paths for a specific event. So please come by the poster if you're interested in discussing some of these statistical approaches for propagation modeling.
Good morning, I'm Cengiz Tonik from Hungary, and my poster is about the Central and Eastern European Infrasound Network, which is a collaboration established last year between Ukraine, Austria, Hungary, and Romania, and the Czech Republic. And on this poster, we were investigating about how much improvement this network causes for the detection capability of the European network. So for the details, please check my poster.
Okay, so many papers explain that when you have a discrepancy between observed and predicted infrasound, you just have to superimpose suitable disturbance onto the atmospheric specification. And for this, you can use the gravity wave model with two neighbor parameters. But the point is that there is no consensus regarding the values of these parameters, so that you can use the infrasound detections to update these parameters using full wave modeling and machine learning techniques. Here what you have is on this figure the zonal mean temperature at a given location, starting with a global climate model which exhibits a strong warm bias. And you can reduce this temperature bias by using a new gravity wave model which is calibrated using infrasound detection at Hukakiro. Thank you. You can come to this poster. Okay, so that's under the poster with a PhD student, Alexandre Goupy, and a colleague, Didier Lecor. In fact, the question is, how can you model complexity of wave propagation using a simple polynomial? Is this even possible? And that's what we did. We use, in fact, a polynomial to represent wave propagation, complexity of wave propagation. And for this, we use the generalized polynomial chaos. So I can assure you that it works, and come to this poster to have some information about the method.
Thank you.
Good morning. I am Paulina Bittner, and I represent the analysts from the International Data Center. What we did was to look at about 50 REB events with large number of infrasound associations, and we were interested in first to see what could be the sources of these events. So you have two representatives in the slide. Then we were interested where these events happen, when they happen, and whether the large number of associated phases would guarantee a good location. We also saw that propagation conditions and wind at the station have played a large role in the detectability of these infrasound events. Please come to my poster if you are interested in analysis of our events. Thank you very much.
Well, good morning. I'm Rodrigo De Negri. I'm working with Roman Matosa. We are trying to develop statistical lookup tables for the IMS stations. What I'm doing here is to analyze 3 big VI4 eruptions in Chile. In particular, here you see Cuyo Cordon Cauye. And we want to have a robust lookup tables to know how much the winds will change the apparent azimuth in our IMS stations. So if you're interested in my work, you're welcome to poster. P21, yes, I thought it was P26, but well, I'm sorry. Come and we can discuss about my work here today, 2:30 to 3:30 p.m. Thank you.
So that's a work with Jean-François Mafouf and a PhD student, Pierre van der Becken. So turning noise into useful data is the dream of every geophysicist. And that's what we try to do here by using a Tunisian station. And we use ray tracing simulations and observations made at the IMS stations in order to select, in fact, the correct number within an ensemble provided by the Météo France in France.
Okay, so I just want you to remember weather uncertainty affects radionuclide transport. So if weather uncertainty wasn't important, you wouldn't see a whole lot of colors over on the right-hand side. Please come to poster P23 if you're interested.
Okay, this is poster P26. At BGR, we processed the full IMS infrasound data set with a new processing, or with different processing configurations. The newest one is the 3rd octave frequency bands. And this allows us to get more accurate signal parameters, to identify more sources or more detections for specific sources. And on the next slide, I will then show the second part. So this is the first part, P26. And on the second part, P27, we will show you examples and how this fully reprocessed data set can contribute to the monitoring of the stratospheric dynamics using microbiomes, but also to monitor other atmospheric dynamics, such as the mountain-associated waves. So if you're interested what is behind this figure, then please find Lars or me at posters P26 and P27 in the afternoon. Thank you.
Thank you very much. So that concludes the morning session of T1.1. So I just want to remind the poster presenters and all of you that to be at the posters between 2:30 and 3:30 upstairs. And before that, I invite you to join us to listen to the highlight talk by Michel Jean at 2 p.m. about the dynamic of the atmosphere. And we will restart T1.1 in this room at 3:30. So see you in the afternoon. And don't forget to vote.
Okay. Okay, so.
Donc maintenant on a une pause. Oui.
Oui, 15h30.
On revient ici à 3h30.
Oui, 3h30.